Hey guys, this is Salman. I'm back with a new topic that is stresses in curved beam. So it is an important topic. As you have seen in the last video, I have covered what is curved beam, differences between curved beam and straight beam, what are the assumptions made in finding stress distribution for a curved flexural member, and now we are going to see stresses in curved beam. In the next video, I'm going to make stress in closed ring. So these are very important topics. So without wasting time, let's go. So stresses in curved beam. As I told, this is an important derivation, so we need to know what is it. Okay, so we'll start. Consider a curved beam subjected to a bending moment MB as shown in figure. So this is the curved beam, so which is subjected to a bending moment. Until and unless we won't apply an bending moment, it will not be curved. So okay, so we'll see in figure the lines AB. You can see a lines AB and CD represent two such planes before bending. So I'll tell you one example. See, this is our beam, actual beam. So if this is a straight beam, so when in a figure as they told, the line AB and CD are the two such plane, okay, before bending. So before bending it will be like this, okay. Then when there is a no stresses induced at this position, okay. So when a bending moment MB is applied to the beam, the plane CD rotates with respect to AB to an angle d theta, so to the position FG. So as when a CD, when a bending moment is applied, the CD will rotates, the plane CD will rotates with respect to the AB through an angle d theta. So it will be like this, okay. This is our A, this is B, and this is C, and this is D. So there will be an angle generated over here, that is d theta. So I'll take it as FG, okay. So and the outer fibers are shortened while the inner fiber are elongated. So this is the outer fiber, okay. This is the outer fiber and this is the inner fiber. So outer fiber is shortened. So once it is there, then the outer fiber is shortened as the inner, while the inner fibers are elongated. So the original length of the strip at the distance y from the neutral axis is y plus r and theta. So the original length of the strip at a distance y from the neutral axis is y plus r n theta. You should remember this, y plus r n by theta. So this is y, okay. It is shortened by the amount of y d theta. So shortened by an amount of y d theta. So y d theta by y plus r n theta, that is nothing but E. And the stresses in the fiber is sigma is equal to capital E into small e, where we know this sigma is nothing but a stress, this is a strain, and this is our Young's modulus. So the equation becomes that is sigma is equals to minus e y d theta by y plus r n theta. So remember this, y d theta by y plus r n theta. So I'll take it as equation number 1. Okay, so as you can see here, so you can see this is the compressive, where the distribution of stresses at compressive and tensile, it will look like this. This is our centroidal and neutral axis, this is our beam, these are the two such planes. When it has been when a bending moment is applied, there will be a angle d theta will produce. This you can see, this is a theta, RO, RC, RN, RI. We'll see what are this. Okay. So let MB is the applied bending moment. So MB is the applied bending moment. RI is the inner radius of curved beam. So this is the inner, this is the outer. So RI, where is RI? This here is the RI. So inner radius of the curved beam, from where the center line of curvature. Okay. Then RO. RO is nothing but outer radius of a curved beam. So this is the outer radius. So this is the outer radius of the curved beam. This is RO. Okay. Then RC, radius of centroidal axis. So this is the RC, radius of centroidal. As I told, this is the centroidal axis. This is the neutral axis. So radius of centroidal axis. Rn is the radius of neutral axis. So now as I told, that is sigma is equals to minus E y d theta by y plus r n theta. This is equation number 1. Okay, since the fiber is shortened, the stress induced in the fiber is compressive stress. So since it is shortened, so the stress induces compressive stress, hence the negative sign I have taken here. This is a negative sign because a compressive stress was there. Okay, the load on the strip having dy and cross section area dA is dF. Okay, so that is, now this equation will become dF is equals to sigma dA is equals to minus, same you have to write, into dA. Okay, now that is integration of dF is equals to 0. Now integration of this term, this whole term is equals to 0. E d theta by theta, integration of this, we remains with y dA by y plus Rn. Okay, Rn. So integrate this term is equals to 0. So as E d theta by theta is not equal to 0, and this integration of y dA by y plus Rn is equals to 0. Understood till this? Now this you take it as equation number 2. Okay, no, I'll tell you where is the equation number 2. So MB, now we have to do is, if the moment are taken about the neutral axis, we have to take a moment, that is bending moment, is equals to minus integration of y df. Substitute the value of df. Now what is the value of df? This is the value of df. Okay, now MB is equals to E d theta by theta integration of y square by y plus Rn dA. So now if you differentiate this, it will be y minus y Rn divided by y plus Rn into dA. Now E d theta integration of y dA. Okay, integration of y dA. Now what is y dA? I'll tell you afterwards. But y dA by y plus Rn is equals to 0, as I told before. So take it as equation number 2. Okay, now this, since integration of YDA represents the statical moment of area, it may be replaced by capital A. This is capital A. Okay, it may be replaced by capital A small e. So this capital A is nothing but total area, and the distance, this E is nothing but the distance E from the centroidal axis to neutral axis. So wherever YDA was there, we have to replace with AE. So the equation becomes MB is equals to E d theta. This is AE. Integration of YDA, that was a statical moment of area. So I have replaced with AE. So directly you can write AE. This is an equation number 3rd. Now from equation number 1, E d theta. Now we have to take a remove E d theta. I'll show you. Here you can see a equation number 1. You have to take it E d theta by theta. So you'll get, by rearranging, you'll get, that is minus sigma y plus Rn by y. Now substitute this term in equation number 3rd. If you substitute, you'll get MB is equals to minus sigma y plus Rn by y into AE. Now what is sigma? Sigma is equals to minus MBY y plus Rn into AE. This is our equation number 4. Similarly, we have to find two, that is bending stress at the outer fiber and bending stress at the inner fiber. So what is bending stress at the outer fiber? We'll see. Bending stress at the outer fiber, sigma BO. Sigma BO means, sigma B means bending stress, O means outer fiber. So sigma BO is equals to minus MB CO divided by AE into Rn plus CO, where Rn plus CO is nothing but RO. So I'll replace like this: sigma BO is equals to minus MB by CO divided by AE into RO. This is my equation number 5. Okay, so as CO is nothing but the distance from the neutral axis to the outer fiber, so it is a compressive stress, as I taken negative sign. Okay, so what is it is? So distance CO, you can see here, this is CI, this is CO. Okay, so this is C1, C2. So CO is nothing but the distance from the neutral axis to the outer fiber. This is the neutral axis to the outer fiber. Okay, similarly CI is nothing but distance from the neutral axis to the inner fiber. I'll show you. See here. Now we'll move to the next, that is bending stress at the inner fiber. So this is sigma bi. Sigma b is nothing but bending stress at the inner fiber. I is equals to mbci by ae rn minus ci. Now where rn minus ci is nothing but ri. Okay, rn minus ci is equal to ri. So substitute in this, where ci is, as I told, distance from the neutral axis to the inner fiber. As you can see, I have taken I didn't took a positive negative sign because it is a tensile stress, so hence positive sign. So this is up to this only. The derivation is, first you have to draw the diagram, and then you have to write that, consider a beam like that, then when you apply a bending moment, this you can see a stresses distribution. This is a compressive and this is the tensile. When the bending moment is applied, the plane which is AB and CD, you have to take two such planes. Then once the bending moment is applied, it will rotate with respect to AB with an angle d theta, that is FG. Okay, then similarly this is curvature. I have forgot to tell, this is CL. CL is nothing but center line of curvature. I have drawn plain line here, actually it is like this. Okay, center line of curvature. Okay, make it correct. Then similarly this I told, sigma is equals to capital E minus capital E into small e. Okay, then this term, and when the load on the strip having the thickness dy and cross sectional area dA is df, then df is equals to dA, here also dA, the integration of dA, take e d theta by theta outside, integration of only y dA by y plus rn is equals to 0, where this is not equal to 0 and this is equal to 0. Okay, then we have to apply a moments. So if you apply a moments, mb is equals to minus integration of y df, substitute the value of df, you'll get this term. Once you get this term differentiate, then what you have to do is this y integration of y dA by y plus rn is equals to 0, take it as equation number 2. So here integration of y dA is nothing but statical moment of area, that is y dA. We have to replace y dA, integration of y dA by ae. So replace integration of y dA by ae, then mb is equals to e d theta by theta into ae. This is our equation number 3rd. Now from the equation number 1 we want e d theta by theta. So this is the e d theta, we have to take it e d theta. You'll after rearrange, so you'll get this equation, that is minus sigma y plus rn by y. So from the equation 1, we found that e d theta by theta, that is minus sigma y plus rn by y. Substitute this equation in equation number 3. So mb is equals to minus sigma y plus rn by y into ae. Now we want sigma. Sigma is equals to minus mby by y plus rn into ae. This is equation number 4. Now we have to find, as I told, that is outer fiber and inner fiber. So this is the term you'll get. Okay. So guys, this is the very important question and it is very easy also if you do. So please practice this derivation, and next after this I'll solve the problems and then I'll turn to the I'll teach that stresses in a closed ring. So before that I'll teach problems on the stresses in a curved beam. So please work on it. So thank you for watching. Have a good day.